Okay, today's video is looking at mutually exclusivity or mutually exclusive events. First thing you need to do is, if you haven't done so already, is watch the Dr. Nick video from start to finish. Covers all the details you need to know and links it with the previous lesson with complementary events. So once you've done that, come back to this video and where we go through some of the questions. So just to try and summarize some of the things around mutually exclusivity, is that we talk about events where they're not the same. In previous lessons, I've talked about looking at Venn diagrams in terms of the classes you're in, so maths, English. So those things are not mutually exclusive, so you can do maths and English. When we talk about mutual exclusivity, it's a good idea to think about as kaitiaki classes or form classes, that they are mutually exclusive. You can only be in one. You can't be in two different classes. So when that's the case, we talk about the intersection being empty. So that's why the two eggs in the Venn diagram don't overlap and are separated. Now, the whole point of this is that it doesn't come out too much apart from looking at it as a test to see what type of formula you use for the union of two events. So in other words, the probability of A or B. Now, if things are not mutually exclusive, we use this red formula where there's an overlap here. Is why we have to use this, take it away the intersection of them both. For mutually exclusive events, it's really easy. When you add their individual probabilities together, they should add up to what the union value or the OR value is. So that tends to be the question type you tend to get is blah 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 event is not mutually exclusive. Work out the probability of A or B. And that means that you just have to use this formula. Or the other one is say it proved these events are mutually exclusive. Whereas you should be able to just add the individual probabilities and get your answer. So if we take a look at some questions, really simply, which of the following pairs of events are mutually exclusive? So I'll give you a moment to take a look at these and you make your choice. There may be more than one. Okay, so hopefully you gave that a go. So let's take a look at A. So cards, ace and spades. So the big question you've got to ask yourself, is it possible that you can select a card that is an ace and a spades? Well, no, you can't. It's either an ace or a spade. It's not both. The way to make this question that they're not mutually exclusive. So in other words, sorry, I'm going with that is mutually exclusive because you can't get a card that's an ace and a spade unless it's a wild card. So we're assuming that it's a normal pack of 52 cards. But if you were having a set of cards and you're drawing two, is it possible? Yes, that would be possible to have an ace and a spade. Looking at B, odd and even are mutually exclusive. There is no odd value that's also an even value. There are no even values that are also odd values. Sitting down and standing up, they're mutually exclusive. You're either sat down or stood up. Sitting down and scratch your nose, they're not mutually exclusive. You can do both of those at the times. You can be sat down and scratching your nose. So these are the types of questions you need to be asking yourself when mutual exclusivity comes into it. Is can you have both happen at the same time? So here is a key question. So in a class of 29 children, 15 like history, 21 like maths, at least one of the two. They all like at least one of the two subjects. So in other words, there's nobody who doesn't like history or maths. What is the probability that a child chosen at random likes maths but not history? So, key thing is this is error, but I'm not going to do that. So I've got my two events. So we're going to use the Venn diagram. So you've got history, you've got maths. We know that there are 0 people on the outside because you are told all like at least one of the two. So the big question you've got to ask yourself, is this mutually exclusive? No, it's not. You can be in a history class and a maths class, and we certainly haven't been told otherwise. So if we take a look at these numbers, 15 plus 21 gives us 36. So what that means is that we've got 36 results by adding them together, but 29 in the class. So, hang on. So 36 take away 29 gives us 7. So it means there must be 7 people that like both, because they're being counted twice in this 15 in this 21. So then it's a really easy calculation. It should be 15 take away 7 gives us 8 people like just history, and then 21 take away 7 gives us 14 just like maths. So the probability that a child chosen at random likes maths but not history is 14 out of 29. And that's our answer. So while that's not necessarily usually mutual exclusivity, the fact that we know that it's not means that we can use that that we add them up. So if it was a test to say whether they were mutually exclusive, the number of people who like history plus the number of people who like maths should have added up to 29. The last type of question is, and this tends to be relatively popular in the exam, is giving you some numbers, then you have to use the formula to test whether something's mutually exclusive. So remember, the formula states that A plus B, probability of A plus B must equal A or B if they are mutually exclusive. Okay, so if we take a look at A, is it mutually exclusive? Well, we've got 0.2, 0.3 equals 0.5. That means that these events are mutually exclusive. If we take a look at the next one, we've got 0.31 plus 0.14. So they don't add up to 0.59. They add up to 0.45. So they're not mutually exclusive. Again, look at C. So first of all, we've got 0.29 plus 0.16. If you add them together, you do get 0.45, but you should have noticed that we've got the intersection sign. So that's not the rule, it's only for or. If something's mutually exclusive, it should be added to 0, equals 0. So that's not mutually exclusive as well. Looking at the last one, we don't know the probability of A, we know that the probability of B is 0.6, so we can't add those together, but the information we've got is that the intersection is equal to 0, so therefore it has to be mutually exclusive. Because we know it's mutually exclusive, we can use the formula at the top here to then say, well, this must be 0.15, because if it's mutually exclusive, that this A value plus the B value must equal 0.75. Sorry. So there's a worksheet on the lesson page that covers a lot of those things. It'd be a good idea to work your way through that. So just summarizing again, some of the things. Key thing is this formula for non-mutually exclusive events, but for mutually exclusive events, it's that formula. Okay, go to that lesson page and get that done.